Good afternoon, all. Let us start the session on GATE training program. We are going to discuss the topic linear data structures stack, so which comes under programming and data structures. This is D. Lakshmi from Department of CSE. So on this GATE training program, let us start the session. So the topics we are going to cover today are stack ADT, that is operations regarding stack data structure, applications of stack, which covers evaluating arithmetic expressions, conversion of infix to postfix expression. So let us see what is nothing but stack. A stack is a linear data structure that follows last in first out principle. So the element which is inserted at the last will comes out first from the structure. So insertion and deletion can be done at only one end of the stack called the top of the stack. We have the pointer known as top of the stack where we are going to insert the element or where we are going to delete the element from the stack. So example is given as pile of coins and stack of trays. We can take the coins are arranged one above the other. We can arrange the notebook one above the other. We can say many examples. So here it is mentioned with a pile of coins and stack of trays. So here the diagram shows the top of the stack, a stack data structure, and top pointer. So it is always point to the first element inserted at the stack. For empty stack, the top position is going to always point out -1. That is below the index level of an array. So whenever we take the array for inserting the elements one above the other, it shows that with following the stack properties. When the stack is empty, the top pointer is going to point out -1. And then, as I said, the examples are pile of coins. Here also, the real life examples of stack to understand its structure is assignment of files, ring, spool, and gun magazines. So here we can understand the stack data structure in better way. We are placing the ball one above the other. We are placing the ball, first red ball above the yellow ball and the blue ball. So which is inserted at the last is blue ball. That blue ball will be taken out first from the stack. So the last inserted element or thing or item can be deleted out first. So that is followed by the stack. So there are two main operations, two fundamental operations performed on the stack. They are push and pop operations. So push is nothing but inserting a new element at the top of the stack. So it is a process of inserting a new element at the top of the stack. And pop is obviously is going to be deleting the element. So for every push operation, we are going to check for the full stack. That is whether when the stack is full, we cannot insert any new element at the stack, right? So so we need to check the full stack that whether the stack overflows or not before inserting any element. So for each and every insertion of an element into the stack, we need to increment the top pointer by 1. So that is known as top is equal to top plus 1. So pop is nothing but it is a process of deleting the top element of the stack. For every pop operation, we need to check the condition that whether the stack underflows. Underflow means in the empty stack we cannot delete any element. There are no elements to be deleted, right? So we need to check the empty stack underflow. So delete or pop the top element x from the stack and decrement the top by minus. For each and every pop operation or delete operation, the top pointer is going to be decremented by 1. So when we compare the push and pop operation, for every push operation, top pointer will be incremented by 1. For every pop operation, the top pointer is going to be decremented by 1. So these are the two exceptional conditions given for stack. One is stack overflow and stack underflow. So stack overflows is an attempt to insert an element X when the stack is full and it is said to be stack overflow. For every push operation, we need to check this condition. For stack underflow, we need to check the stack underflow condition when we are going to delete an element. So it is an attempt to delete an element when the stack is empty. Is said to be stack underflow. So how the stack can be implemented? Stack can be implemented in two ways. First one is array implementation of stack, and next one is linked list implementation of stack. So array implementation of stack is obviously static implementation, whereas linked list implementation is dynamic implementation. So the size for array implementation of stack, the stack size is fixed, whereas in case of linked list implementation, the stack size is going to vary during the runtime. For array implementation of stack, each stack is associated with a top pointer. For empty stack, top is equal to -1 and stack is declared with its maximum size. So here it is given array declaration of stack. So define array size 5 or int variable name array size. So this size 5 is fixed for that stack. So we can insert only 5 elements at the maximum. This size cannot be changed. So operations on stack empty operation. So initially stack is empty. With empty stack, top pointer points to -1. It is necessary to check the empty stack before deleting an element from the stack. So deletion is nothing but pop operation. So for every pop operation, we need to check for this empty condition. So routine to check whether the stack is empty. So int is empty. The function is called with the name of the function is given as is empty. We are going to pass the an array stack, that is stack yes. So stack full operation. As we keep inserting the elements, the stack gets filled with the elements. Hence, it is necessary to check whether the stack is full or not before inserting a new element into the stack. So return to check whether the stack is full. So here we have some elements already inserted in the stack, which is a full stack. So we have inserted 10, 20, 30, 40, 50. Since we have 5, size of the array is 5, we have inserted 5 elements. So the top of the stack obviously points to index 4, since the array size starts with 0. So this last element is going to be the top is equal to 4, which contains 50. Now, so in order to check whether the stack is full, we can call this routine. And this routine checks whether the stack is filled or not, whether the stack is filled or not. So next one, if top is equal to array size -1. Array size is 5, 5 minus 1 is 4, since the last index is 4. So here return 1. So if this condition is satisfied, it indicates that the stack is filled with some set of elements. So next one, push operation. It is a process of inserting a new element at the top of the stack. It takes two parameters, push x comma s. So x is nothing but the element to be inserted, and s is the name of the stack. So push x comma s, the element x to be inserted at the top of the stack s. Before inserting an element into the stack, check for full stack. If the stack is already full, insertion is not possible. Otherwise, increment the top pointer by 1 and then insert the element x at the top of the stack. So we are going to push the element 10 at a stack yes. So what happens? It gets inserted. So push next one is we are going to insert 20, the element 20, so which gets inserted at the top of 10. So after 10, we are inserting 20, and then we are going to insert 30, the element 30. So we have inserted 10, 20 and 30 into the stack. So routine to push an element into the stack. So here we are calling the function push since it has two parameters x comma s. If top is equal to array size minus 1, then obviously it is going to display the message stack is full, insertion is not possible. Else top is equal to top plus 1. Obviously top pointer gets incremented by 1, and we are going to insert in that top position the element data gets inserted. So s of top is equal to x. If a top position is 3, means s of 3 is equal to x. The x is the data to be inserted. Next one, let us discuss about pop operation. It is a process of deleting the top element of the stack. It takes only one parameter, pop of x, the element x to be deleted from the top of the stack. Before deleting the top element of the stack, check for empty stack. If the stack is empty, deletion is not possible. Otherwise, delete the top element from the stack and then decrement the top pointer by 1. So since we have the full stack which gets inserted 10, 20, 30, 40, 50, pop 50. So obviously when you decrement the top pointer by 1, the top pointer is going to point out that data 40 which is available at the index 4. So top is equal to top minus 1. Here it shows the top is going to point out the array index 4, which array index 3, which contains the data 40. So here is a routine for the deletion operation, that is pop the top element of the stack. So void pop if top is equal to minus 1. That means that the stack is empty. We cannot delete any element. So here it is going to display the message empty stack, deletion is not possible. Else the elements is going to be get deleted. So x is equal to s of top and top is equal to top minus 1. So x, the element which gets deleted will be assigned to the variable x. Now return top element. So in order to find out, for example, if the array size is 50, we have inserted only 20 elements. The top of the stack is going to point out the last element, that is 20th element we have inserted. In order to find out where the top pointer is, we need to have the procedure known as return top element. So if the user needs to know the last element inserted into the stack, then the user can return the top element of the stack. To do this, first check for empty stack. If the stack is empty, then there is no element in the stack. Otherwise, return the element which is pointed by the top pointer in the stack. Now, when the stack is empty, top is equal to minus 1. When the stack is full, the last index value is 4 here. The top is going to point out that fourth index value. So routine to return top of a top element of the stack is if top is equal to minus 1, displays the message there are no elements in the stack. It returns 0. Else it goes for return s of top. So s of top is stack of top. Top is 4 here. It returns the value 4. So this we have seen the array implementation of stack, where we can apply the properties or rules of stack using the array. So in normal array, we can insert the element at any position. We can remove the element from any position, right? So in case of this array implementation of stack, we need to apply the rules or properties of stack. Only the element can be inserted only the last position, whereas the element can also be removed only from the topmost position, that is the last position. So applying the same set of rules for linked list also, that is discussed under linked list implementation of stack. So stack elements are implemented using singly linked list concept. Dynamically, memory is allocated to each element of the stack as a node. So type declaration for stack using singly linked list. This is the declaration part given for the linked list implementation of stack. We need to create a dynamic data structure, that is with a two field. One field is going to point one field is going to hold the data for the stack, and another field is going to point the address of the next node. So each and every node is going to have two field. And here in this linked list concept, we are going to apply the rules of properties of a stack. So this is the declaration part given for linked list implementation of stack. So what are the operations we are going to perform? Whether we are going to check whether the stack is empty, we are going to do the push operation, pop operation, and we are going to check the topmost element of the stack. As we have seen in the array implementation also, here the same thing we are going to follow in linked list implementation. So we need to have four procedures or four operations written for the stack. So one is empty, one is push, and another one is pop, and last one is top element. So stack empty operation. So initially stack is empty. So with the linked list implementation, empty stack is represented as S of next is equal to null. Here S represents the header node. So in a single linked list, always the header node points to the first node of the linked list. Since the first node is known, we can traverse along the uh, further nodes or remaining nodes till the end of the linked list. So we need to know the first node. The first node is always denoted as the header node. So this header node here is pointed as S. Obviously, we don't have any stack initially. S of next is equal to null. This is assigned to null. So it is necessary to check for empty stack before deleting an element from the stack. If it is null, now we can understand that the stack is empty. So routine to check whether the stack is empty, int is empty, S of stack. If S of next is equal to null, return 1. So obviously there is no address in the header node. So it is not at all pointing out any stack. That is the meaning. So S of next is equal to null means it returns the value. So then it indicates that the stack is empty. Next, push operation. It is a process of inserting a new element at the top of the stack. With the linked list implementation, a new element is always inserted at the front of the list. That is S of next. So here, since in the previous operation, we have seen S of next is equal to null. Now here we are going to assign some address. That address is going to be the first node of the stack. The first element we have inserted in the stack. So it takes two parameters, push of x comma s. The element x to be inserted at the top of the stack s. So steps are to be followed. Allocate the memory for the new node to be inserted. Insert the element in the data field of the new node. Update the next field of the new node with the address of the next node stored in the s of next. So here is the push operation. Now we are having one example diagram. The first element of the stack is 30, the second element is 20, and the third element is 10. Obviously, when we are inserting the element will be always inserted at the previous. Whenever we have only one element, the next element should be inserted at its previous position. The next element will be inserted at its previous position. This procedure is keep on followed. So the first inserted element in the stack is 10 here. After that, we are inserting 20. After that, we are inserting 30. So 30 is the last element. The last element, obviously, it is going to be available at the topmost position of the stack. So see here, 30. So when we are trying to insert the element 40, the 40 should be inserted before 30. The 40 is going to be the topmost element. So when the header is pointing out the 30 before, now the header has to point out the 40 element 40. Since the 40 is the last inserted element, that is the topmost element in the stack. It is considered as the topmost element in the stack. So the header file address must be point out the last inserted element 40, that is shown in the diagram. So routine to push an element. So we are allocating the memory using each and every node is created by the structure. The name of the structure is declared as given as node here. So by referring this struct node, we are going to allocate the memory, and that memory, newly allocated memory address will be assigned to new node. So uh, new node of data field gets the value x, and new node of next gets the s of next. So s of next address, s of next is assigned to new node of next, and s of next is equal to new node. Now the header node is going to point out the first node we have created. That first node we have created address is assigned to new node. So S of next is equal to new node. Now obviously we have, since we have only one node we have created so far, that new node is going to be the top node. So the top pointer is going to point out the new node. Now, when you call this push operation again and again, when you call this push operations one more time, again the next new node will be created, memory will be allocated, it gets the data, and then S of next is going to point out the new node. So the topmost value, the topmost pointer is going to keep on changing whenever we are creating a new node at each and every time. So this is the pop operation explanation given for pop operations. We all know very well. Pop operation is process of deleting the top element of the stack. With linked list implementation, that element at the front of the list S of next is always deleted. It takes only one parameter, pop of X. The element X to be deleted from the front of the list. Before deleting the front element in the list, check for empty stack. The stack is empty, deletion is not possible. Otherwise, make the front element in the list as temp. So the same procedure we have followed for as we have followed for array also. Here in array, each and every location, the topmost location element gets decremented. Here the topmost node must be removed from the stack. So here the example given, uh, we have four elements 40, 30, 20 and 10. 40 is the topmost element which is pointed out the header file, and now we are trying to, in the header file address is assigned to 30th element 30, that is the second node. Obviously we should consider that this 40 element 40 gets removed or deleted out of the stack. So we have, at last we have 30, 20 and 10 in my stack structure. So this is the routine given for pop operation. So question temp top is equal to S of next. If S of next not equal to null means empty stack, pop not possible. So else temp is equal to S of next. S of next is equal to temp of next. The element which we are going to delete is going to be pointed out by temp pointer temp. So the node to be deleted will be freed at last. The memory will be deallocated. In this diagram, it is shown clearly. Next one is return top element. If the user needs to know the last element inserted into the stack, then the user can return the top element of the stack. And to do this, first check for empty stack. If the stack is empty, then there is no element in the stack. Otherwise, return the element present in the S of next of data in the list. Now, yes, since I have told that this S is going to be the header node, it always points to the first node of the list. So here the first node of the stack is going to be the last inserted element, right? Always yes. So which we when we want to know the return top element, need to know the topmost element. That address will be given to the S pointer, right? The S pointer next of data is going to have the value. So routine to return top element. S of next not equal to null. Error stack is empty. Return 0, else return S of next of data. So S of next is the first node of the stack, so which contains some data. That data gets displayed by means of this routine. So applications of stack, it's very important topic. Here the following are some of the applications of stack. Evaluating the arithmetic expression. Under that we have conversion of infix to postfix expression, evaluating the postfix expression, balancing the symbols, function called Tower of Hanoi 8 queen problem. So there are various applications. These are the most important applications of stack. So here first one is evaluating the arithmetic expression, conversion of infix to postfix expression, and evaluating the postfix expression. So there are three types of expressions. When we take any expression, it has three types: infix expression, postfix expression, prefix expression. So infix is arithmetic operator appears between the two operands to which it is being applied. That is operand 1 operator and operand 2. So here the example given is a slash b plus c. Here the operands are a, b and c. So between these two operands, we have one operator. Between the operator A, operand A and B, we have the operator slash. Between the operand B and C, we have the operator plus. So it is the kind of infix expression. So next one is postfix expression. The arithmetic operator appears directly after the two operands to which it applies. It also is called as a reverse Polish notation. That is operand 1, operand 2 and operator. Now we have in the given expression, first it starts with any operand, any two operands, then only it has the operator. So here infix expression is given a slash b plus c. When we convert it into postfix, we get the answer as ab slash c plus. For operand 1, operand 2 operator, operand 1 is a, operand 2 is b, and operator is slash. Likewise, operand 1 is C and operator is plus. So the operator comes at the end of the given expression. That kind of expression is nothing but postfix expression. Last one is prefix expression. The prefix, the arithmetic operator is placed before the two operands to which it is applied, also called Polish notation. Here we have operator, operand 1 and operand 2. So here when you take the same example, the operator comes first, then only it is followed by operands. So plus slash ABC. So whenever you take any kind of expression, the expression starts with operator means it is a prefix expression. If the expression ends with an operator, that is the postfix expression. If the expression contains the operator in between the operands, then it is the infix expression. Now this is the precedence of operators. Precedence of operators, when you take the parenthesis gets the highest precedence, and inari operator gets the next precedence, and multiplication and division both gets the equal priority, which comes next to the unary operator. And next one is addition subtraction operation, and next one is shift operators, comparison operators, equality operators, bitwise operators, goes like that. So highest priority is given to the parenthesis in the given expression. So here it shows the level of lowest to highest. So the lowest precedence goes to logical OR operator. According to this precedence of operators, the conversion of the infix expression to postfix expression will be followed using stack. So let us see some example problems for converting the infix expression to postfix expression. So here the algorithm is given for this conversion using stack. First read the infix expression one character at a time until it encounters a delimiter hashtag. So whenever you take any expression, that expression should end with the hashtag. It means that that is the end of the given expression. If the character is an operand, place it in the output. If the character is an operator, push it onto the stack. If the stack operator is a higher or equal priority, then the operator pop that operator from the stack on and place it onto the output. So we have several steps to be followed. Step 1, step 2, step 3, and step 4 given for conversion of infix to postfix expression. Using this algorithm, we are going to convert the given infix expression into postfix expression. Finally, we get the output. That output is going to be the postfix expression. Now let us see one example. That example is a asterisk b plus c minus d slash e hashtag. So here this hashtag denotes the end of the given expression. So let us read the character one by one. Character A is read. It is not going to be pushed into the stack. It will becomes in the output. Okay. So here, if the operator, if you read, if the character operators are read, that only will be pushed into the stack. Next is asterisk. So obviously asterisk is an operator. So that operator will be pushed inside the stack. Next comes operand. Operand is B. That operand is going to be given to the output. So up to this step, we have read three characters. First one is operand, second one is operator, and third one is operand. First operand is A, which is given to the output. Second one is operator, which is given to the stack, and third one is operand B, which is given to the output. So at this stage, the output contains AB, the stack contains asterisk. So next is plus operator. Now when you are having plus, so we cannot place a plus above the asterisk, since asterisk has the highest priority than the plus operator. So asterisk has to be popped out to the output. We can place plus into the stack. That is what shown. So at present stack contains plus operator. After plus, open parenthesis is given to the stack. Till the closed parenthesis is encountered, it will be available into the stack. After open parenthesis, we have the operand C. That operand C is placed into the output. So next one is minus. So minus comes above the open parenthesis. So till close parenthesis is encountered, the open parenthesis will be available in the stack. Whatever be it as highest priority or lowest priority, whatever it is, it should be placed on the stack above the open parenthesis. After that, the operand D is read, so that is given to the output. So the output now contains AB star or asterisk CD. Now next to D, slash operator. Slash operator is given to the stack. So slash has the highest priority over minus, slash comes into the stack. So next comes E. So E is the operand. E is given to the output. So at this stage, the output contains A, B, asterisk, C, D, E. The stack contains plus, open parenthesis, minus, and slash. Next is the closed parenthesis. As I said, when the closed parenthesis encountered, up to the open parenthesis, all the elements will be popped out of the stack. So here in the output, we have that operators alone, not the open parenthesis and closed parenthesis, as per the algorithm given for this conversion of infix to postfix expression. So it encounters the hashtag at last. So it tries to empty the stack. So the stack at last contains plus operators. The plus operator comes to the output at last. So the answer is going to be AB asterisk CDE slash minus plus. So for applying these rules, we can solve any kind of such problems like given infix expressions will be converted into postfix expression using stack. So there are some problems to practice. So that is A plus B star C plus D slash F plus D star key. So we have some problems also here. And next application of stack is evaluating the arithmetic expression. Under evaluating the arithmetic expression, we have evaluating the postfix expression. So for our first one, we have seen as conversion of infix to postfix expression. Second one is evaluating the postfix expression. Here the algorithm is explained. Convert the expression in reverse Polish notation, that is postfix notation. Read the postfix expression one character at a time until it encounters a delimiter hashtag. If the character is an operand, push its associated value onto the stack. If the character is an operator, pop two values from the stack and apply that operator for those two values and push the result again into the stack. So let us see one example. Here infix notation is given as 2 plus 4 asterisk 4 plus 6. Now before going this with this evaluating the arithmetic expression, let us check whether the given expression is the postfix expression. If not, we need to convert that given expression into postfix first. So here we are converting this infix notation into postfix notation. So we have 24 plus 2 4 plus 4 6 plus asterisk. So with this postfix notation only, we are going for the evaluation. Now what is the first character? 2 2 is pushed onto the stack. What is the second character? 4 4 is again pushed onto the stack. So what is the third character? Third character is the operator, which is obviously applied to the previous two elements, which is pushed onto the stack. The previous two elements pushed onto the stack are 2 and 4. So apply this plus 2 plus for 2 and 4, which gives the answer as 6. Now this 6 is pushed onto the stack. After pushing 6, the next character red is 4. So that 4 is pushed onto the stack. After pushing 4, again we have 6. This 6 will be pushed onto the stack. Now, after this 4 and 6, we have the plus operator. Plus operator will be applied to the previous two inserted, that is last two inserted element of stack. The last two inserted element of stack are 4 and 6. Apply this plus for 4 and 6. So 4 and 6 becomes 10 now. Now, push this result into the stack again. So already we have 6 in the stack. Above 6, we have pushed 10 also. And finally, we have one asterisk operator. This asterisk operator is applied to the previous two elements of stack. The previous two elements of stack are 10 and 6. So 10 and into 6 gives 60. The answer is going to be 60. 60 will be pushed inside the stack. So the given expression is evaluated. The answer is given as 60 at last. So the result is going to be 60. So consider the obtained postfix expression. We have another example, AB star CDE slash minus plus. Now they have given some number for each and every operand. For A, they have assigned the value 2. For B, they have assigned the value 3. For C, they have assigned the value 4. For D, also 4. For E, the value assigned is 2. So when you take this example, the answer is going to be 8. So using the stack, after this evaluation of this arithmetic expression, we get the result as 8 at last. So next application of stack is balancing the symbols. So any expressions can be given with the open parenthesis, the open bracket, open square bracket, curly bracket, whatever it is, closed curly bracket. So we are going to check whether the given expression is balanced or not. That is leftmost parenthesis or balances with the rightmost parenthesis. At the left side, for the given expression, at the left side, if I have 3 parentheses, the right side also it contains it must have 3 parentheses. That is 3 open parentheses means we need to have 3 closed parentheses. Likewise, if we have 3 square brackets, at the right side also we need to have 3 square brackets. So whether the given expression is balanced or not, whether the expression is balanced or not using stack, that is what the next application is going to be. So compilers checks the program for errors. A lack of one symbol will cause an error. A program that checks whether everything is balanced. Every right parenthesis should have its left parenthesis. Check for balancing the parenthesis, brackets, braces, and ignore any other character. So this is the algorithm. Read one character at a time until it encounters the delimiter hashtag. If the character is an opening symbol, push it onto the stack. If the character is a closing symbol and if the stack is empty, and report an error as a missing opening symbol. If it is closing symbol and if it has corresponding opening symbol in the stack, pop it from the stack. Otherwise, report an error as mismatched symbol. So here we have various steps given for balancing the symbols. The algorithm contains various steps. Following the steps, we are going to see one example. So let us see, consider the expression. Given expression b asterisk b minus 4 asterisk a asterisk c slash 2 asterisk a. Whether we are going to check whether this given expression is balanced or not. So at the left side we have 2 open parentheses. At the right side we have only one closed parenthesis. When you see it directly, we can say, so there is one open curly bracket, equally there is one closed curly bracket. There is one square bracket, equally we have one left square bracket and right square bracket. So this curly brackets and square brackets are balanced, but this open parenthesis is not balanced, right or not? So we are going to check whether the given expression is balanced or not using stack. So read the character. First open parenthesis, which is given to the stack. Second open parenthesis, again it is given to the stack. And third one is And third character is one closed curly bracket. So one closed curly bracket is there, one opened curly bracket will be popped out from the stack, and next one is one open curly bracket, and that is given to the stack. Next one is closed curly bracket. Obviously, that open curly bracket goes out of the stack since it is balanced. We have only one open parenthesis inside the stack. Next one is we have one square bracket. That square bracket will be pushed into the stack. Again, another square bracket will be seen. So the open square bracket has the equal match of closed square bracket. Everything is popped out. Only it contains only one open parenthesis. One. So at last, when we read all the characters, the stack should be empty. Here, the stack is not at all empty. So we have only one open parenthesis here. At last, when you go for the delimited hashtag, one closed parenthesis comes. So obviously it matches with one open parenthesis in the stack, so we are going to have the empty stack. Hence the symbols are balanced in the given expression. So the given expression is the balanced expression. The given expression is the balanced expression. So let us discuss the gate questions on stack data structure. Um, the best data structure uh, to check whether an arithmetic expression is balanced parenthesis is a stack. So just now we have seen that application. Obviously, the answer is going to be the stack. So for balancing the parenthesis or balancing the symbols, we are going to use the data structure known as stack. Here, the answer stack is marked in green color. That is the answer for the given question. So next one is, consider the following sequence of operations on an empty stack: push 54, push 52, pop, push 55, push 62, and S is equal to pop. Consider the following sequence of operations on an empty queue. So NQ21. So here both stack and queue questions are asked as a one question here. Let us see the stack part alone. So we are going to push the element 54. We are going to push the element 52. So stack, empty stack contains first element is 54 and the next element is 52. We are going to perform pop operation. So pop operation is what? So we are going to pop one value. So what is the topmost value? 52 is going to be the topmost value which is popped out. Now the stack contains only 54. Then we are pushing 55. So above 54 we have 55, and then we are pushing 62. So we have 54, 55, and 62 onto the stack, right or not? So we have only three elements. Likewise, in queue data structure also, they are inserting some elements in the queue. They are removing some elements from the queue. So we need to combine this um, stack value and then queue value. At last, we need to find out the answer. Likewise, the question is asked. So when you discuss about the queue data structure, this question can be answered, right? So whenever you take a stack alone here, the stack alone value contains only pop. S is equal to pop. So which elements get popped out? 62 gets popped out. So 62 will be popped out. Here, when you take Q contains 21, next to 24. DQ means which element comes out first. The element which is inserted first comes out first in the case of Q. So 21 gets deleted. Then again, 24 and 28 is available. 24, 28, and 32. So when you remove 24, so here we are removing 24. So in the stack we are removing 62. In the queue we are removing 28. So S plus Q gives 62 plus 28, right? So the answer is going to be, so the answer is shown in the slide. So we can work out this problem. We can work out by drawing the stack structure and queue structure. We can find out the answer at last. So this kind of questions are frequently asked in the gate So here gets next comes the following postfix expression single digit operands is evaluated using a stack 823 exponent slash 23 asterisk plus 51 asterisk. So note that the exponent is the exponential operator, that is a cap is the exponential operation that top two elements of the stack after the first asterisk is evaluated are. Now, when you work out this problem using the algorithm of evaluating the postfix expression, so the answer we are getting is 6 comma 1. The top two elements, what are the two topmost elements available in the stack after the first asterisk is evaluated? Now, in the given expression, we have two asterisks. One asterisk comes after 2 3 and another asterisk comes after 5 1. So they are asking that after 2 3, when the asterisk is applied, what are the two topmost elements available in the stack? So the answer is going to be 6 comma 1. So when you work out this problem, we'll get the answer as 6 comma 1. So which of the following is essential for converting an infix expression to postfix form efficiently? So that is the operator stack. So this here conversion of infix to postfix expression obviously deals with the operators for the given expression. So we need to have the operator stack. So answer is an operator stack. Next one, the postfix expression for the infix expression a plus b asterisk c plus d slash f plus b f plus d asterisk e. So some expression is given infix expression. We need to convert the given infix expression into postfix using stack. So when you apply the algorithm given for infix to postfix conversion using stack, we get the answer a b c d plus asterisk f slash plus d asterisk plus, that is the option B. So your answer is going to be option B. So which of the following permutations can be obtained in the input in the same order using a stack, assuming that the input is the sequence 1 2 3 4 5 in that order? Now when you take this question, we are so following permutation, we are having the answer 3 4 5 2 1, that is 1 2 3 4. Now when you take they are inserting the element as 1 2 3 4 5. Obviously when you apply the permutation rule, what happens, the answer is going to be 3 4 5 2 1. So the option B is the correct answer. So next one is the following sequence of operations is performed on stack: a push of 10, push of 20, pop, push of 10, push of 20, pop, 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 push of 20, and pop. So first we are going to push the element 10, and then we are going to push the element 20. So the stack contains 10 above 20. After that we are performing pop element. The topmost element is 20. 20 gets popped out or removed from out of the stack. Now the stack contains only the element 10. Again we are pushing 10, so the stack now contains 10 and then 20. So now the stack contains 10 above 10 and then 20. Okay, and then we are performing three pop operations. So all the elements get removed, then we are pushing element 20, then pop. The sequence of the value popped out is the sequence of the value popped out. At last we have popped out one value 20. Before that we have popped out again 20. We have popped out 110 and 110. So the order is 20 20 10 10 and 20. So the answer is going to be the option B. When you work out this problem by drawing the stack structure, try to push the elements one by one and pop. When the pop operation is given, pop the elements. At last in the stack, the pop order is 20 20 10 10 and 20. So next question is assume that the operators plus, minus, asterisk or left associative and the exponent is the right associative. The order of precedence from highest to lowest is associative, asterisk, plus and minus. The postfix expression corresponding to the infix expression a plus b asterisk c minus d exponent e exponent f is the answer is a b c asterisk plus d e f exponent and minus. When you work out this problem, you'll get the answer option A as your answer. And the result evaluating the postfix expression, again we are applying the same application of stack, converting the given evaluating the postfix expression. The expression is given here. When we evaluate it, we get the final result as 142. So option C is the answer. So we have discussed some gate questions here. We have discussed some gate questions asked in the previous years regarding the stack data structure. All of you try to work out this kind of problems to get the correct answer. Okay, so when you work out it, you can find out the answer. By seeing it, we cannot give any proper answer. So the answer may be confusing. All the options may look like the same. You have to select one proper correct answer after working out the given problem. Thank you all students for your cooperation. Hope it was useful. This session will be useful for you. Thank you all. Thank you for your cooperation. Thank you so much.